So I'd like to thank Christian, Antun, and all of the organizers for their work in putting together this wonderful program and for the invitation to come and be part of it. If Georgia were able to join us today, I'm sure she would be delighted to see all of the interesting new mathematics and also very happy to see the inclusive and supportive community that she helped to grow. Georgia began her mathematics career as a student at Ohio State University in the late 1960s. She always said that Ohio State had an excellent undergraduate honors program, though she also mentioned that the honors students were used as cannon fodder and required to stand in a line between student protesters and police during anti-war demonstrations. Given that Georgia graduated in 1970, the same year as the Ohio National Guard opened fire on the protesters at Kent State University. This is in itself quite incredible. Georgia published her first math paper while an undergraduate at Ohio State. This was published in the Pi Mu Epsilon undergraduate journal. It was not only an introduction to mathematical research, but unfortunately also an introduction into gender politics and discrimination when a well-meaning but misguided editor decided to edit her name in the final publication, which you can see here. In spite of this, she had a stellar career. Publishing 135 publications with well over 1,000 citations and close to 100 co-authors. She was, yes. What is, pardon? Oh, Erdős number. Erdős number is, of Georgia, you're asking. Let me think for a moment. I think it was number 2 or 3 would be my best guess. Perhaps through some of her recent work, actually, with what is his name? Stanford University, an excellent statistician, and yes. Perhaps through there. I really don't know. Anyway, she mentored 22 PhD students and hundreds of young mathematicians, was a past president of this organization, AMS Central Section Secretary and editor of many important journals in algebra, and served on many committees of the AMS, the NSF, the MSRI Board of Directors, grants panels for NSF and the Canadian NSF as well. For those who didn't have the privilege to know her, I can say that Georgia was an excellent mathematician, an exceptional mentor, and contributor to the wider community, and really an absolutely first-rate human being. Yes, after finishing at Ohio State, she went to Yale University to work with Nathan Jacobson. She was proud of her distinguished family career, tree, and included it in her introductory Lie algebra courses. At the time, Jacobson was working to introduce Jordan techniques into Lie theory. For those who are completely unfamiliar with Jordan algebras, my apologies for those who aren't, the definition of a Jordan algebra is quite simple. It's a general non-associative algebra. Here I'm assuming characteristic not 2 for some technical reasons, otherwise things become much more complicated. But we can linearize if we're outside of characteristic 2. And Jordan algebra is just something that is a commutative algebra and obeys this rather weak associativity property. So the example to have in mind is that just like you can build a Lie algebra out of any associative algebra by introducing a Lie product of AB minus BA, you can do the symmetric product for a Jordan algebra. And these Jordan algebras, as well as their Jordan subalgebras, are known as special. It turns out that almost all simple Jordan algebras are special. Those which aren't special are called exceptional. So it's a manifestation of this Garrison Keillor's Lake Wobegon principle, where the women are strong, the men are good looking, and all the children are above average. The key introduction of how Jordan theory comes into Lie theory was rather new at the time. Hitt, Cantor, and Kusher had introduced a construction by which you could take any Jordan algebra and build a Lie algebra out of it, essentially taking 3 copies of the Jordan algebra. You can think about SL2, but having entries in the Jordan algebra. But because of non-associativity, that's not going to be closed under the natural B bracket. So you need to add a bit more. There are various versions of the TKK construction. The one that I have on the screen here is the universal central extension version. The BCA here, that mysterious thing, that is the associator. So this means that BC times A minus B times CA, which of course is not necessarily 0 when dealing with a non-associative algebra. It turns out that every A1 being the root system of SL2 graded Lie algebra is a central quotient of one of these. So you look at one of these TKK algebras, you mod out by some subalgebra of the center, and you can construct every A1 graded Lie algebra through this construction. Jacobson used this construction with great success in order to come up with concrete realizations of the exceptional Lie algebras, notably E6, E7, E8. George's thesis was part of this program. George's PhD thesis dealt with inner ideals. Again, because Jordan algebras are commutative, the notion of left and right ideal doesn't make a lot of sense. So in order to expand the number of ideals and thereby strengthen the Artinian property, they introduced new ideals called inner ideals. So this terminology is quite natural when dealing with special Jordan algebras. The idea is that you put your Jordan algebra J inside your Jordan algebra B, or your supposed inner ideal B, and make sure that it gets preserved under this multiplication. So an example of this is in the case of associative algebras, any one-sided ideal for the associative algebra becomes an inner ideal for A+, which you can think for 2 seconds and you'll see that this is true. So it's kind of a Jordan notion of one-sided ideal. So it turned out that finite dimensionality looked to be a bit too strong. Artinian looked to be a bit too weak. But if you increase the number of ideals, then Artinian becomes a stronger condition, and then you can work towards structure theory. So on the suggestion of Seligman, Benkart wrote her PhD thesis on a Lie analog of this. So of course she took the natural definition of what an inner ideal ought to be based on that Jordan definition you see above. And in a non-trivial example, well, a trivial example, Padet, I'm having trouble. Used to teaching in French. Okay, so an example is you look at the positive part of SL2, and that's an inner ideal and very far from being an ideal. So this, she wrote up into what I would call her first grand slam of a paper, which included her PhD results as well as going quite a bit further, which was published in 1977 in Transactions. So she classifies the minimal inner ideals in Lie algebras in terms of what are called absolute zero divisors. These are certain ad nilpotent elements of the Lie algebra. She went further and used ad nilpotent elements to find Jordan algebras inside the Lie algebra. So essentially, she looked for ad nilpotent elements of nilpotent length 3 in order to pick out copies of SL2 that were living in there, and look for the modules of these Jordan algebras living inside too, in order to get a structure theorem. So this turned out to be quite prescient, both for her later work on classification of root-graded Lie algebras, which I'll get to in a moment, as well as one of the first steps towards the classification of finite dimensional simple Lie algebras in characteristic P. This paper was very influential and amazingly continues to be influential. When I was looking up her various papers on MathSciNet, I noted that this paper has 6 citations since 2020. Which is quite amazing given the age of the paper. After her PhD at Yale, she was hired as one of the inaugural class of C.C. McDuffie instructors at the University of Wisconsin. This was meant to be a prestigious 2-year postdoc. At the time of her retirement conference in 2008, Lou Solomon revealed that, in fact, the professors in Madison had agreed in advance that no McDuffie instructor would ever be hired into a tenure track position at Madison as a way to make sure that they didn't become too insular and always hired from the outside. However, he said, Georgia managed to solve every single mathematical problem the algebraists could throw away. And so the faculty at Wisconsin broke the rule as soon as they made it and hired her into a tenure track position in 1976. At this time, it was exceedingly rare for women to hold tenure track positions at top US universities. But amazingly, Georgia was not the first to be hired into a tenure track position at Wisconsin. This distinction goes to Mary Ellen Rudin, who Georgia loved dearly and regarded as a role model. By the time I was a graduate student at Wisconsin, Mary Ellen was long retired, but still she was a presence in the department, full of energy and friendliness. And she made the time to talk to each and every one of the graduate students and ask us about our theses, which she listened to with great interest, even when it was very far from her own research area of point set topology. Her most prolific early collaborations were with Marshall Osborne, with whom she co-authored 16 published papers. Osborne and Benkart worked together initially in looking at some what would now be termed as exotic non-associative algebras, but gradually the research focused more and more precisely on the problem of classification of finite dimensional simple Lie algebras in characteristic P. The classification of finite dimensional simple Lie algebras in characteristic 0 over an algebraically closed field is a story of root systems. And my apologies to, from what I've seen in the other talks, perhaps the majority of the audience who are quite familiar with this. You can take a little mental break for the next two minutes while I tell the small number of non-initiated people in the audience about root systems. So you start with a finite dimensional simple Lie algebra over C. So you can think an example of this is to look at the n by n complex matrices together with this product, which is AB minus BA. Your matrices are A and B. This is an example of a finite dimensional simple Lie algebra over C. And you take a Cartan subalgebra. So in the example that I just gave, an example of the Cartan subalgebra would be look at the diagonal matrices with trace 0. The whole raison d'etre of the Cartan subalgebra is in order to make a common eigenspace decomposition of the Lie algebra. So the Cartan subalgebra is a maximal submodule with respect to the property that relative to the Lie multiplication, the action is semi-simple on the Lie algebra. So the Lie algebra decomposes into common eigenspaces, the 0 eigenspace, and here are all of the non-zero eigenspaces grouped together. The collection of generalized eigenvalues which are generalized eigenvalues is called the root system of the Lie algebra. In fact, it doesn't depend on the choice of Cartan subalgebra, but that's a result rather than an obvious statement. The rank of the Lie algebra can be defined to be the dimension of the Cartan subalgebra, or equivalently the rank of the lattice spanned by this root system. The result is that the isomorphism classes of finite dimensional simple Lie algebras over C are in bijection with the isomorphism classes of irreducible root systems. And then you can make something called Dynkin diagrams and use some Euclidean geometry in order to classify the irreducible root systems. It turns out that there are 4 infinite families of Lie algebras corresponding to these SLN series, the even and odd size matrix of orthogonals Lie algebras and the symplectic Lie algebras. And then there are 5 exceptionals. Just like in the classification of finite simple groups, you have these 26 sporadic groups. You have 5 exceptional Lie algebras. Okay, so end of pause. Now we go back to characteristic P. Serious progress began to be made in characteristic P with the Kostrikhin-Shafarevich conjecture in 1966. They conjectured that the so-called restricted finite dimensional simple Lie algebras over an algebraically closed field of relatively small, still characteristic, were of classical type or Cartan type. So classical type just means that you take these finite dimensional simple Lie algebras that we know over C and you reduce them mod P. So more precisely, you take a nice generating set for these Lie algebras in which all of your structure constants are integers, which allows you to tensor over the integers with this field. And this is what mod P reduction amounts to in classical Lie algebras. In Cartan type is again motivated by the characteristic 0 situation. And you have various infinite dimensional Lie algebras, which are said to be of Cartan type. For example, the derivations of the Laurent polynomial ring and several variables. So this is sort of a finite dimensional counterpart of this that works because you're in characteristic P. And so this Witt series together with the special Hamiltonian and contact series. Bloch and Wilson showed in 1984 that in fact the Kostrikhin-Shafarevich conjecture is true in characteristic bigger than 7. Benkart and Osborne studied the much more difficult problem of looking at unrestricted Lie algebras in finite characteristic. They showed that the Kostrikhin-Shafarevich conjecture holds, again, with this characteristic restriction that it'd be bigger than 7, if we enlarge the truncated current algebras that are appearing in the definition of the Witt algebras to include more divided powers. So you can just think of this as instead of modding out by xi to the p, you're modding out by xi to something bigger. It's a little more complicated than that, but that's the intuition here. So this they did for rank 1 Lie algebras. You can think, okay, big deal, rank 1 is just SL2, but no, in characteristic P, you have others. So for example, you have the Witt algebra in one variable is another rank 1 finite dimensional Lie algebra in characteristic P. This paper was quite important, appearing in Annals in 1984, and was in some together with the Bloch-Wilson paper I just mentioned, these sort of formed the basis for the work that followed. Eventually, the proofs in this paper were absorbed into work of Premet, Strata, and Wilson in 2004, where they announced the classification that, in fact, essentially the Kostrikhin-Shafarevich conjecture was correct, except in characteristic 5, there was a new type of Lie algebra that hadn't been anticipated, the Malikian type Lie algebra. However, their proof relies on one missing piece. The missing piece is the so-called recognition theorem. So the recognition theorem was announced and given a partial proof by Katz way back in 1970. This was not quite correct since it missed the Malikian type, for example. And the final complete proof for the result, it only appeared in 2009 in a paper of Georgia together with Gregory and Premet. At the same time as she was studying characteristic P structure theory, she was also delving into infinite dimensional representation theory for finite dimensional Lie algebras in characteristic 0 and structure theory for infinite dimensional Lie algebras in characteristic 0. The work on, again, pause for the experts, sorry. The work on the infinite dimensional representation theory of finite dimensional Lie algebras in characteristic 0 is about weight modules. And this was done primarily with her two close friends and good collaborators, Dan Britton and Frank Lemire. So a weight module is just a module, generally infinite dimensional here, you understand, in which this Cartan subalgebra acts, again, semi-simply and decomposes the module into, in this case, we're going to require finite dimensional subspaces, common eigenspaces for the action of the elements. The first big result in this direction was the PhD thesis of Georgia's first student, Surin Fernando, in his 1983 PhD thesis, which he later published in Transactions in 1990, said that if you want to find a simple weight module for a finite dimensional simple Lie algebra in characteristic 0, you can do this by using parabolic induction. So parabolic induction is a generalization of the Verma construction for modules, which you may be familiar with from your introductory Lie algebra class. So a parabolic subalgebra, part of the definition is it has to include the Borel subalgebra. So an example of a parabolic is the Borel subalgebra itself. So you can just think of the upper triangular matrices in the case of trace 0, in the case of SLN. And in that case, you know that the finite dimensional simple modules for a solvable Lie algebra are going to be one-dimensional. So this N here is just a one-dimensional space, and you have exactly the Verma module here. So it turns out that in order to get all the weight modules, you need something a bit more general. And you need to consider the weight modules for various parabolic subalgebras. And we can also assume that N is cuspidal, meaning it doesn't come from a smaller parabolic, an induction from a smaller parabolic. And that's equivalent to the dimensions of the weight spaces being constant. With Dan Britton and Frank Lemire, they showed that these infinite dimensional cuspidal modules, i.e. the new situation that can possibly occur, occurs only in type A and C, so only special linear and symplectic Lie algebras. They looked at the case as Dan and Frank had previously looked at of what they called pointed modules. So these are modules in which the weight spaces are at most one-dimensional, and it gave a construction to explain how these modules come from modules from the Weyl algebra. The final classification was announced by Olivier Mathieu in 2000, well, proved by Olivier Mathieu in 2000, and it amounts to classifying the cuspidals in type A and type C, building on the work of Fernando, Georgia, Britton, and Lemire. Here's a photo of Georgia together with Frank Lemire and Dan Britton, and this is Susan, Dan's wife, Eleanor, Frank's wife, and Paula is Georgia's sister. And here's Goofy and Georgia and Frank Lemire in Disneyland from many years before this photo was taken. Yes, in terms of the infinite dimensional structure theory, Georgia was looking at what are called root-graded Lie algebras. So a root-graded Lie algebra is now, again, generally an infinite dimensional Lie algebra, which contains some sort of finite dimensional grading algebra within it. So it's delta graded, delta being the root system, if it's graded by delta, and also satisfies this technical condition that the zero component is generated by the bracket of the various non-zero root spaces. So the key idea is that the Lie algebra, if it's delta graded, can be decomposed into a direct sum of various submodules here. So the G here you should think of as the adjoint module for G for itself, because you know that the weights for this, because it's root graded here, you know the weights are very limited. The weights have to be within the root system itself. So you have copies of the adjoint module, copies of the little adjoint module, and then you have a bunch of trivial modules grouped together. So the classification amounts to figuring out what A, B, and D can occur here, and how do you get the multiplication between these components. So this was done type by type. So initially for simply lace type by Steve Behrman and Bob Moody in '92. Then the big jump was to do this in the case of the non-simply laced finite dimensional Lie algebras. And this required generalizations of the Tip-Cantor-Kusher construction to other non-associative algebras. And it's really a festival of non-associative algebras in the Benkart Yefim-Zelmanov paper in '96. And then this Nair did the A1 case, Allison Benkart Gao. We're dealing with so-called non-reduced root system BC, except for BC1, which was later done by Georgia and Smirnov. As a Canadian mathematician, I should mention that most of these people involved in these past two projects are Canadians. And Georgia at that time was making many trips back and forth between Madison and various points in Canada, Windsor to see Dan and Frank, and various places in the prairies to see Steve Behrman and Bob Moody were in Saskatchewan at the time, and Bruce Allison is at University of Alberta. However, Georgia's involvement in Canadian mathematics went much further than that. She was heavily involved in mathematical organization and politics in Canada as well. She organized many, many conferences and spoke in even more conferences in Canada over the years. In fact, my own first real conference I went to, she was one of the main speakers. It was a 3-week-long summer school in Edmonton. And this was it was a wonderful experience. She recommended that I try to go, and I went, and it influenced the whole future trajectory of my own mathematical career. She also even served on committees within Canada and helped us navigate tricky political situations. She spoke to various deans and other important people to convince them that yes, they should really help out mathematics, and gave advice with very wise diplomacy over the years. Amazingly, I believe she had a similarly strong relationship with both Spain and South Korea. and at about the same time, which is just really amazing for an American mathematician to have a significant influence on at least 3 countries on 3 continents. So here she is with the Spanish crowd here. Alberto El Duque was one of her major collaborators on Jordan type things, and Seokjin Kang, with whom she did extensive work on quantum groups and crystal bases, and her former student Dong Ho Moon, who is a combinatorial representation theorist in Korea. As an example of one of the sticky situations that she helped with, Georgia told me that she was organizing a conference with Seokjin Kang, and they had sent off a funding application to the Korean government. Some government bureaucrat sent back the funding application with a polite but pointed request for further information and asked, why should we spend public money on a conference dedicated to the theory of dishonesty? So then she had to write back and explain the origins of Lie theory. And she said to me, well, it's really a good thing I didn't mention the killing form. So I'd now like to talk a bit about her mentoring activities, because I think this is what really made Georgia special. Here's a list of her PhD students according to math genealogy in chronological order. I'll come back to this in a moment. Here are some photographs of PhD students. This is Oliver Ng, Chanyang Lee, Tom Halverson, Manish Chakrabarti, Steve Cass, again, Oliver, Mark Hall, and Dong Ho Moon again. Here are some of her more recent students, Matt Bloss, Dina Christodoulopoulos, Matt Andres, Cheryl Grood, Samuel Lopes, Sarah Madariaga, Shantala Mukherjee, and myself with my own student, Xiaohe. My apologies to the others. Those are the ones I was easily able to lift off the internet. That's not at all a complete photograph, but the list of students is complete over here. So yeah, when I came to Madison on the advice of her student, Cheryl Grood, who told me that I should definitely choose Madison over the other schools I was considering, because Georgia was absolutely the best advisor you could have. I didn't really know what this meant as the first and only person in my family to go to graduate school. I wasn't quite sure what an advisor was, but I took Cheryl's advice and I never regretted it. When I asked Georgia if she would be my supervisor, she gave me an appointment for a few days later in her office. So I thought, okay, I've got to come with a PhD project planned. So I went to Katz's book because I knew Katz's infinite dimensional Lie algebras book had open problems. So I looked through Katz's book. I looked at all the starred problems. I read the statements very carefully and looked at the background in case I was tested on that. And I concluded that the most accessible problem was looking at root multiplicities in hyperbolic Kac-Moody algebras. So I walked into her office and I announced that I wanted to calculate root multiplicities for hyperbolic Kac-Moody algebras. Georgia managed to solemnly listen to me through that and not burst out laughing. And she said, well, that might be difficult. So instead she said, why don't you just come to my group meetings with my other PhD students and we'll see how it goes from there. At the time, she already had 4 other PhD students. You see, I was somewhat the second of her large cohorts of PhD students she had. And yeah, in the end, I ended up working on something rather different than root multiplicities of hyperbolic Kac-Moody algebras, something more mathematical physics, to which she said, be careful what you hope for, was her exact line on that. But in her first large cohort of PhD students, back here in the late 80s, early 90s, she did something which at the time was quite unusual, but it's become much more common today, is she initiated a large collaboration with her 5 PhD students at the time, looking at Schur-Weil duality for mixed tensor products, GLN actions on mixed tensor products of the natural module. So again, my apologies to those in this audience who are far more expert than I am on this, but I talked for a moment about Schur-Weil duality. So the idea of classical Schur-Weyl duality, as envisioned by Schur and by Weyl, is to look at the natural module for GLR here, and look at the diagonal action on the n-fold tensor product of the natural module. You also have a right action by the symmetric group on this tensor product in the obvious way. You just permute factors. And the miracle, the beautiful thing here is that the SN action here actually generates the centralizer of the GLR action, and vice versa. The GLR action generates the centralizer of the SN action. And you can play off these two commuting actions in order to decompose the module into sums of simples and get some correspondences between certain finite dimensional simple modules for SN and for GLR. This has been generalized in various directions. So I mentioned some of the most famous directions. One is to restrict to smaller subgroups. So you start with GLR, you can look at the orthogonal matrices inside there and ask, is there a similar mutual commutator property for the orthogonal group? And the answer is yes. Brouwer introduced what's now called the Brouwer algebra, in part because the fact that it's the Schur-Weyl dual, it is the mutual centralizer of these actions on these natural modules around 1930. So as you expect, when you shrink this, you have to increase this size here because centralizing a smaller thing is a weaker condition than centralizing the big thing. And the Brouwer algebra is given a diagrammatical calculus similar to looking at the braid diagrams which define the symmetric group multiplication. You can shrink further down to the symmetric group itself. The permutation matrices are certainly orthogonal, so they live in the orthogonal group here. And around 1990, it was found that the Schur-Weyl dual of that is the partition algebra. So it's spanned by all of the partitions of 2n elements with a certain multiplication that, again, is defined diagrammatically. So this large collaboration that I had mentioned with Manish Chakrabarty, Tom Halverson, Rob Leduc, Jianyang Li, and Jeff Stromer was to try to determine the Schur-Weyl dual, in which instead of looking at the action on V, the n-fold tensor product of V, we in fact look at the mixed tensor product, so V and V star. And they found the Schur-Weyl dual, and which is now called the Wald-Brouwer algebra, and has appeared in other settings as well more recently, for example, in quantum groups and in Lie superalgebras. And there are numerous further variations and generalizations by Georgia. This was one of her favorite topics, which she did often in collaborations with younger mathematicians. I mentioned especially Tom Halverson, with whom she wrote many papers on related topics. Georgia had a knack for finding interesting mathematics. She would propose some sort of problem to you, and you'd think, or at least I would, this is really unmotivated and uninteresting, very accessible, but maybe not so significant. But then you start working on it and you find out that it's related to this. Oh, and this, and this, and this. And then after a while, you find out that, in fact, it's part of this large, beautiful picture and connected to things all over the place. So one of my regrets is I never asked her, did she actually know that from the beginning? Or was she also discovering this along the way? Was it just her cleverness that let her find the interesting and the beautiful in starting with almost anything? So in her later years, after retirement, she devoted an increasing amount of energy and time towards promoting and supporting women working in the mathematical sciences. And in some ways, you can think of this large group collaboration as a model for some things that she organized later. So again, I'm very hesitant to say too much about this, as many of you were actual members of these large group collaboration projects. I put the conference photos for 3 of these working groups in which Georgia was a co-organizer. I know she also participated in several other such programs as a group leader or as a simple participant, particularly, for example, I know Ann Schilling organized one, I think, in 2017, which Georgia participated in and led to a couple joint papers with the members of the collaboration group. Yes. So Unfortunately, time is running out, and I haven't had time to talk about many of Georgia's other very important, some of her most important contributions to mathematics. At the time when I was her student, she was very enamored of down-up algebras, which is a concept that she introduced in order to try to capture what is special about SL2 theory and Bial algebras and the like to explain their large role in representation theory. I remember she came back from MSRI one time, and you have to picture this was in a classroom situation. She stood at the front of the class and she said, "I noticed the elevator at MSRI, it says only up on it. But then when I look upside down, it says down, up, down, up." And this was an example of her kind of sense of humor, that she was so charmed by this by this kind of observation. Anyway, she wrote a very important paper on this together with Tom Roby. She did important work on Hopf algebras and quantum groups with Sarah Witherspoon and with many other people. And I'm not able to get to that, nor to the work that she did in these collaborations here. But maybe it's a good thing, since many of you are better placed than I am to talk about the mathematics and also Georgia's role in these collaborative projects. I have a terrible habit of writing people letters, and then I never get around to going and buying stamps. And I put them in a drawer at my desk, and after a few years pass, they continue to gather dust, and they never get sent. So I'd like to end this talk with a letter that I never sent to Georgia, and I will always regret having never sent on the occasion of her retirement. So this is from January 2008. Dear Georgia, I will add to the chorus of voices wishing you congratulations on your 60th birthday and your graduation to emeritus status. As many others have doubtless said, you are an inspiration and example to all of us in your excellent research, patient mentoring, high standards of personal and professional ethics, and your genuine compassion and warmth. I take special delight in your sense of humor, from Chaco Leibniz's to Minnesotan rigor mortis, to the up-down of the MSRI elevator. I am deeply grateful for your willingness to take the time to seriously listen and share your advice, even when the question has nothing to do with math. In short, congratulations and thank you, and may we have many more good years with you in the space of states and provinces. With much admiration, Michael. Yes. Please.
I was a graduate student.
Perhaps you'd like to use the microphone.
I was a graduate student of Charlie Conley at Madison when Georgia arrived. And I just want to add a footnote about Mary Ellen Rudin's tenure. She went from being instructor to full professor overnight because there had been an anti-nepotism law in Wisconsin, and it took an act of the state legislature to invalidate that so that Mary Ellen could get tenure. That's one footnote. And the other thing is Georgia was an avid tennis player, and she and I played tennis for about a year and a half while I finished my dissertation. And we met at least once a week, sometimes twice a week, as early as 7:30 or 8 o'clock in the morning, so we could finish playing before classes started. So she was much better than me in tennis as well.